So we're going to talk a little bit about what happens when, instead of having a charge traveling through the air or something like that, we've got charge traveling along a wire. The formula is a little different, but the force is the same. So this is the magnetic force on a current-carrying wire. Again, the charges are just moving down a wire instead of moving through the air. If you remember, the Lorentz force was just QVB sine theta, right? And so we're just going to, once again, I've created, this is a piece of a wire here, and I have a magnetic field pointing out of the board, but it could be pointing in any direction. For convenience, it's out of the board so that the direction of the flow of the charges, the motion of the charges, is this way, and the magnetic field is this way, and so the sine theta is just going to be 1, because theta is 90 degrees. And so if we break these terms down, the magnetic field is just B. Well, the velocity is just delta x over delta t. If I have a little charge here, delta q, which is just a little section of my wire, it's just a little charges in that little section, and I'll call it delta q, then its average velocity down the wire is delta x over the time it takes to move that delta x. And so it's delta x over delta t. So instead of writing that as q, I can say, look, the force is equal to delta q times delta x over delta t times b sine theta. And I can just rearrange this a little bit. This is delta q over delta t times delta x b sine theta. Delta q over delta t is just the current, right? That's just the rate of charge flow. Delta x is how far it's going, and so here we'll just use the length of the wire. And so if I want to know the total charge, the total force on a wire carrying current, my delta x is just going to be the whole length of the wire. And so the Lorentz force just becomes F is equal to I L B sine theta. You can use a uppercase L or a lowercase l, it doesn't matter. And for the magnetic force on a current carrying wire, and so you could see it this way or that way, either one of those. So now we're going to do an example based on our F equals I L B sine theta form of the Lorentz force for charges in wires. And this is a rectangular loop, 10 centimeters by 20 centimeters, carries 8 amps of current as shown. So the current is just cycling around this way. If the magnetic field, which points down the board, is 0.75 Tesla, what's the force on each section? We want the magnitude and direction. And if you notice, it goes A, B, C, D. And so we'll just start with section AB, and we'll say, look, what's the direction? So if you remember, the right-hand rule was put your right arm in the direction of the velocity, and this is kind of hard for me to do, but I'm going to have to lay it this way. And so if I put my right arm in the direction of velocity, and then I curl my fingers towards the magnetic field, the force is going to be into the page, and so I'll say F into the board. Right? And then the magnitude of the force is just I L B sine theta. Well, the direction of the current for this section is that way, and the direction of the magnetic field is this way, so they're at 90 degrees. This term is just 1, and this gives me 8 amps times 0.2 meters times 0.75 Tesla, which is 1.2 newtons. Right, 8 times 0.75 is 6, times 0.2 is 1.2, and so that's my force, right? And so it's 1.2 newtons into the board. If I do CD, conveniently, this section, instead of this one, if I do CD, you're going to notice it has the same current and the same length, and so the force is going to be the same. It's going to be 1.2 newtons. And the only difference is now my current's going this way instead of that way. It's going this way, and when I curve in the direction of the magnetic field, my thumb comes out, and so it's out of the board. Right. And so finally, let's look at these sides. And let's look at BC. BC. Notice the direction of the current is this way, and the direction of the magnetic field is that way. And so F equals I LB sine theta. Theta equals 0, and so this term is just 0. And so there's no force on the sides. Right? This side is moving opposite the direction of the magnetic field, and so its angle is 180 degrees. This is with, its angle is 0 degrees. In both of those cases, the sine is 0, and so the net force is 0. So the force on each wire is 0. So notice that the conclusion we came to was that the force on the two sides is 0, and the force on the top side is directed inward. Right, that's a little arrow pointing in, and then the force on the bottom side is directed outward. And so there's an inward force and an outward force on this, which is trying to twist this this rectangle. This is the principle behind electric motors. You run a current through a wire. It's usually a coil of a whole bunch of wires, and then you do that in the presence of a magnetic field, and with a little trickery you can get this thing to just spin around as a result of the forces on the currents in the wires. And I'll talk about that a little bit next. So now we're going to talk about the torque on a current loop in a magnetic field. And so this is the loop from the last example, except I've kind of put a little axle on it here so it can spin inside this magnetic field like this. And so this would be a side view. So imagine you were looking at it from this direction, right? And that's what this view is. And so the magnetic field's going straight down. And as we showed before, the force was into the board and on the top and out of the board on the bottom, and so it looks like it's to the sides. And you can see the forces on the sides were 0. In this case, they would cancel, so it doesn't matter. But the effect of the magnetic field is to try to twist the coil this way, right, or tumble it that way. And so if it's spinning about this axle, we can calculate the torque. Because if you remember, the formula for the torque is R times F times the sine of the angle between the R and the torque. And so let me erase this and I'll come back to it here in a second. You can look at it if you want to. But the force, so this wire is the wire that the force is on, and this wire, and the current's going around like this, the current I is going around like that, right? It's just going around the loop like this. And so down here the current's going that way, and up here the current's going that way, right? And so it's causing this twisting motion. And way back last semester we learned the formula for torque is R times F times the sine of the angle between them. And so if I'm spinning about this axis, I've just redrawn this over here a little cleaner. Here's my R. If it's going to rotate about this axis, my force is acting up here on the top wire. Again, I'm still looking edge on. And so I'm calling this angle phi, right? And then this is my moment arm. And so if I were to calculate the torque due to this force, the torque is equal to R times F times the sine of the angle between them. Well, what is that? The R is just A over 2, and so it's A over 2. The F is just I times the length of the wire, which is little b, b times the sine of the angle between the R, which is going this way. Remember, for a torque, the R is the distance between the center of rotation and the place when where the force is acting. It's acting along that wire, so in this picture it's that distance. So that's my R. The direction is that direction. The F is this direction, so the angle between them is that phi. And so this is what I get for the torque due to this guy. Turns out this guy produces the same torque because they're both trying to rotate it in the same direction, and it's got the same force on the bottom. And so I'll call that maybe the torque due to the top. And so just the total torque, top plus bottom, is twice that. It's IAB, sorry, write it better, AB times the magnetic field times the sine of the angle between them, and that's equal to I. AB is just the area of the loop. It turns out the loop can have any shape, and you can be a circle or an ellipse or something like that, and the torque is I times the area times the magnetic field times this angle between the slope of the loop and the direction of the force. But it turns out that's the same thing as this angle. Whoops. You can do a little geometry and convince yourself. It's the angle between the perpendicular to the loop and the magnetic field. And so that's how you calculate the torque on a loop. I'll do an example here in a second. So now that we have the formula that the torque is the current times the area times the magnetic field times the sine of the angle between the perpendicular to the loop and the magnetic field, we can use any shape rather than just a rectangle. And so in this problem, a circular loop of wire of radius 0.2 meters. So this is the loop here, right? And that's the radius R, kind of looking at it at an angle, carries current 4 amps. If the perpendicular to the loop makes a 30-degree angle with the magnetic field, in other words, there's the perpendicular to the loop. If it makes a 30-degree angle with the magnetic field, which is 1.5 Tesla, what's the torque on the loop? And I just use the torque is equal to the current times the area of the loop times the magnetic field times the sine of the angle between the perpendicular to the loop and the magnetic field. You might need to know the area of a circle. That's pi r squared. And so it's the current times pi r squared times the magnetic field times the sine of that angle. And so it's 4 amps times pi times 0.2 meters, which is 20 centimeters squared, times 1.5 Tesla times 30 degrees. And so the torque comes out to be, I get 0.38 Newton meters. So it turns out that most loops have multiple turns, and so a coil of wire won't just have one turn, it'll have many turns. And so if you have a coil that looks like this, which is what most magnetic electric motors look like, they have a coil that's got a zillion windings in it, and you want to know the torque on that one, you just multiply by n, where n is the number of coils.